Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH and the equilibrium concentrations for all species present for a solution of known molarity of a strong polyprotic acid. For this problem, we'll calculate the pH and equilibrium concentrations of all species present in a 0.25 molar selenic acid solution at 25 degrees Celsius. Selenic acid is a strong acid, which means it's almost completely dissociated in solution. The first dissociation step for selenic acid is H2SeO4 plus water going to hydronium ion plus HSeO4 minus. And the Ka value for this first dissociation step is very large. It's greater than 1, meaning that it's almost completely dissociated. The second dissociation step for this acid is HSeO4 minus plus water, giving you hydronium ion plus SeO4 2 minus. And the Ka2 value is quite a bit smaller than the Ka1 value. It's 1.2 times 10 to the negative 2. Because selenic acid is essentially 100% dissociated based on the very large Ka value of the first dissociation step, the species present initially do not include H2SeO4 because it pretty much immediately dissociates when it's dissolved in water. So the species present initially then are HSeO4 minus, H3O plus, and this is coming from the first dissociation step where selenic acid completely dissociates into HSeO4 minus and hydronium ions. And you also have, of course, water present as one of the initial species. The first two are acids, and water can act as an acid or a base. Now that you know the acid-base properties of the species initially present, you can think about the possible proton transfer reactions, and there are more than two here, as there have been in other cases. The first you can think about is where HSeO4 minus transfers a proton to water to give you a hydronium ion and SeO4 2 minus. The Ka for this dissociation is 1.2 times 10 to the negative 2. Another possible proton transfer is where you have the hydronium ion donating a proton to a water molecule to give you a hydronium ion, which is what that water molecule becomes when it accepts the proton, and a water molecule, which is what's left over when the hydronium ion, that's the reactant, donates a proton to the water molecule, that's the reactant. And the Ka value for this is equal to 1. Another proton transfer is where a water molecule acting as an acid transfers a proton to another water molecule that's acting as a base to give you a hydronium ion and a hydroxide ion. And the K value for this is the ion product constant of water, which is 1.0 times 10 to the negative 14th. So remember, we're listing all of these possible proton transfer reactions in order to try to define the principal reaction, which is the reaction that's going to head our ice table. So the principal reaction is defined as the reaction with the largest K value. Technically, The second principal reaction has the largest K value. It has a K value of 1. However, this reaction doesn't cause any changes in concentration. As a result, it can't be the principal reaction because remember, we're defining the changes in concentration as X in our ice table, and that's really what we're solving for. So in this case, we take this first reaction as our principal reaction because it has the next largest K value of 1.2 times 10 to the negative 2. So that will be the reaction that will be the principal reaction and the one that will head our ice table. So now we can draw our ice table now that we've decided on the principal reaction. So for our ice table, we have HSeO4 minus plus H2O going to a hydronium ion plus SeO4 2 minus. And we have 3 rows, the initial concentrations, the change in the concentrations to reach equilibrium, and the equilibrium concentrations. We're given in this problem that we're starting with 0.25 molar selenic acid, and because selenic acid itself, so H2SeO4, dissociates into HSeO4 minus plus H3O plus. For every, according to the reaction stoichiometry here, for every 1 mole of selenic acid that dissociates, we get 1 mole of HSeO4 minus and 1 mole of hydronium ion. So therefore, if we have 0.25 molar selenic acid to start, we'll also have 0.25 molar HSeO4 minus and 0.25 molar hydronium ions to start as well. So we can say in our ice table, the HSeO4 minus initial concentration is 0.25. Also, the hydronium concentration initially will be 0.25, and the SeO4 2 minus concentration will start out as 0. So in the change row, we're going to define the change in HSeO4 minus as negative X, and according to the stoichiometry of the balanced equations shown here, for every mole of HSeO4 minus that is lost, we gain 1 mole of H3O plus and 1 mole of SeO4 minus. So on the product side, we'll have plus X and plus X to define the way that the concentration of the products changes. So given all this information, we can now write the equilibrium concentrations for the species present. For HSeO4 minus, we have 0.25 minus X. For the hydronium ion, we have 0.25 plus X. And for SeO4 2 minus, we have X. So now that we have defined the equilibrium concentrations in terms of X, we can use the equilibrium equation for this first dissociation step, which heads our ice table, to solve for X. So the equilibrium equation is Ka is equal to the concentration of H3O plus times the concentration of SeO4 2 minus divided by the concentration of HSeO4 minus. We know that our Ka value is 1.2 times 10 to the negative 2. We can look that up in a table of acid dissociation constants. And then for the concentrations on the right-hand side of the equation, we can substitute in their equilibrium values in terms of X from the ice table. And when we do that, we get 0.25 plus X multiplied by X divided by 0.25 minus X. So in this equation, it would be nice to get rid of both this X and this X, because that would make things much easier to solve. So what we're going to do is make an assumption to try and do that. We're going to assume that 0.25 plus X is approximately equal to 0.25, and also that 0.25 minus x is approximately equal to 0.25. So in both of these cases, we're essentially saying the same thing. We're saying that x is so small that subtracting it or adding it to the initial concentration of selenic acid, which is 0.25, will not make a difference or change that initial concentration. So now we have to test the assumption. So rewriting this equation by incorporating the assumption, we're going to have 1.2 times 10 to the negative 2 is equal to 0.25 times x divided by 0.25. And solving for x is easy here because all we have to do is cancel out the 0.25, and we know that x is equal to 1.2 times 10 to the negative 2. So there's our x value given our assumption. And now that we have that x value, we can substitute it back in to our equilibrium concentrations in terms of x to see if we can actually make this assumption. And if you do the math there, you'll get 0.262, and then if you take 0.25 minus x, that's going to be equal to 0.25 minus 1.2 times 10 to the negative 2, and that's going to give you 0.238. And for this problem, we're rounding to two significant figures. So in our first case, we'll have 0.26, and in the second case here, we'll have 0.24. So for this problem, we actually cannot make this assumption because subtracting x from the initial concentration of 0.25 actually does change that concentration. In one case, it changes it to 0.26, and in the other case of subtraction, it changes it to 0.24. So it's not okay to make the assumption. We have to use the quadratic equation to solve this problem. So what we do is come back to this form and go on and solve from there using the quadratic formula. So we can move the denominator to the other side of the equation to get 0.012 times 0.25 minus x is equal to 0.25 plus x multiplied by x. Getting rid of the parentheses, we're left with 0.003 minus 0.012x is equal to 0.25x plus x squared. So adding 0.012x to both sides of the equation, we'll be left with 0.003 is equal to 0.262x plus x squared, and then subtracting 0.003 from both sides of the equation in order to get our equation in the form we need to find a, b, and c to use the quadratic equation to solve. We'll be left with 0 is equal to x squared plus 0.262x minus 0.003. And you can see from this that a is equal to 1, b is equal to 0.262, and c is equal to negative 0.003. So now we can use the quadratic equation to solve. And the form of the quadratic equation is x is equal to minus b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. So we need to solve for both cases, the case where we're adding and the case where we're subtracting. So first let's solve for the case where we're subtracting. And when we do that, we get x is equal to negative 0.262 minus the square root of 0.262 squared minus 4 times 1 times negative 0.003, and all of that will be divided by 2 times 1. When you do the math here, you get negative 0.273, and then solving for the case where we're adding, we have x is equal to negative 0.262 plus the square root of 0.262 squared minus 4 times 1 times negative 0.003. All of that divided by 2 times a, which is 1. And when you do the math there, you'll get 0.01099. And when you look at these two numbers, one of them is negative, and negative concentrations don't make sense. So we can eliminate that value, and our x value is going to be 0.01099. So now we can go back to our ice table and plug in values to solve for the concentrations of the species present. In our ice table, we've said that HSeO4 minus concentration is equal to 0.25 minus x, so that's going to be 0.25 minus 0.01099, and when you do the math and round to the correct number significant figures, you'll have 0.24 molar. The other concentrations that we need to find include the hydronium ion. So that concentration as designated in the ice table was 0.25 plus x. And then you do the math there, you have 0.25 plus 0.01099, and that's going to give you 0.26 molar, rounded to the correct number of significant figures. We also need to solve for the conjugate base. So that will be the concentration of SeO4 2 minus, and that is equal simply to x. So if we round to the correct number of significant figures, given the x that we found, we'll have 0.01 molar. So there's that concentration. Another one we need to solve for is the hydroxide ion. So we know the relationship Kw is equal to the hydroxide ion concentration times the hydronium ion concentration. Rearranging that, you can say that the hydroxide ion concentration is equal to Kw divided by the hydronium ion concentration, and then Kw is equal to 1.0 times 10 to the negative 14 divided by 0.26099, which is the hydronium ion concentration that we solved for up here, and we're not rounding quite yet, again, so that we don't make a rounding error, and that gives us a hydroxide ion concentration rounded to the correct number of significant figures to be 3.8 times 10 to the negative 14th molar. The last thing we need to do here is find the pH, and we know that the pH is equal to the negative log of the hydronium ion concentration. We've already solved for the hydronium ion concentration, so we're taking the negative log of 0.26099, again not rounding too early to prevent rounding error, and we'll find a pH of 0.58 as our solution. So we found the concentration of all species present, the HSeO4 minus, the hydronium ion, the SeO4 2 minus, the hydroxide ion, and we've also found the pH, so you're done.